Thank you. Let me see. Okay. Yeah, this is joint work with my advisor, Mike Jordan. So the motivating case here is principal component analysis. So I'll be looking at a simple random matrix model that is of this form. It's going to be a matrix W that is rectangular, that is n by m, and it's just an additive rank 1 component to a noise matrix W. And so I'm going to call this rank 1 factor the spike, right? And that's the signal of interest. And I'm interested in either recovering it or testing its presence in the observation Y. Okay, so this is the signal pair. U is n-dimensional, V is m-dimensional. The noise is Gaussian. Beta will be the signal-to-noise ratio of the problem. It will represent the strength of the additive rank 1 component. And I'm dividing here by n so that under a certain, if U and V have a fixed norm, well, if the entries of U and the entries of V are of constant order, the operator norm of these two components are of the same order, so that beta trades off the signal against the noise in the limit. And since the matrix is rectangular, I'm going to assume that the number of columns over the number of rows goes to a certain constant alpha. So this is the high-dimensional limit, which is the most non-trivial one in this case. Some special cases. So if U is equal to V and W is symmetric, this is called the Spikes-Wigner model. It is a slightly simpler model, and we've been able to analyze it very accurately in previous work. Now, if let's suppose that V is also a component that we don't care about, it's just noise, we only care about U, and we assume that V has zero mean and unit variance, this will give us the Spikes covariance model that many of you know. Because the empirical covariance matrix, which is just take the yj's to be the columns of the matrix big Y, look at the empirical covariance matrix, take its expectation, that will be just a spiked rank 1 addition perturbation of the identity. So this is a famous model in statistics. These are special cases. Okay, I'm going to be interested in the detection problem. What is the detection problem? One observes a matrix W with the promise that it is either sampled from this planted model or the spikes model, or it is just complete noise. And you would like to distinguish which is which. Okay? So there are two notions of detection I'll be caring about. There is the notion of strong detection, which just requires the type 1 and type 2 error to go to 0, meaning that your test has to be very confident. In the limits, you have to make 0 errors. And weak detection is not as stringent. It will just minimize this probability of error. If this is not possible, you could just aim for minimizing, for making the least amount of errors possible. Okay? So the questions I'll be asking is, when is strong detection possible? Is it always possible to have a 0 error in the limits? And if it's not, what is the minimum amount of errors you can make? So this is the setting. So let's look at the spectrum. The first thing you could try to do is to look at the singular values of y, or equivalently the eigenvalues of y transpose. This is a plot of these eigenvalues. This is just the density. It is very known, very classical in random matrix theory, is that the first eigenvalue will converge to this, the edge of this bulk if alpha beta squared is smaller than 1. And if alpha beta squared is greater than 1, then we'll have a strictly positive addition to this. And that's the little dots that you see here. So the first eigenvalue will separate from the bulk that is represented by the Marchenko-Pasteur law if and only if alpha beta squared is greater than 1. And that's called the BPP transition following these authors. So strong detection is possible if this is true. If you're above the BPP threshold, you can just look at the spectrum, and that will just give you a reliable test that makes 0 errors in the limits. This is just a sufficient condition, and the main impetus of this work is to understand whether it is also necessary. And there are, so I didn't cite many people that worked on problems of this sort and others, so here's a non-exhaustive list that is by no means exhaustive in this literature. Okay. So I'm considering just a simple binary hypothesis testing problem, and we know what the optimal test is. It's just the likelihood ratio test that takes the Radon-Nikodym derivative of the alternative against the null, and you just look at this likelihood ratio computed and see if it's greater or smaller than 1. and test based on that. So the error of the test is just the sum of the type 1 and type 2 errors, right? And the fact is that this test minimizes this. That's called the name and Pearson lemma. So the whole question boils down to understanding the behavior of L, right? How does it fluctuate? How does it compare to 1? What is the order of magnitude of L? Okay, so the main theorem is the following. So if U and V are drawn from some priors, PU and PV, the coordinates are IID, they have 0 mean, unit variance, and they have bounded supports. If this condition holds, for a k that is specified in the paper, and this k is always greater than or equal to 1, then the log likelihood ratio will be asymptotically normal with this mean and this variance. Here, the plus or minus depends on whether you're under the null or the alternative, right? And we see that the BPP threshold shows up in a natural way inside this logarithm. As you approach the boundary, this will blow up. So this is a strong indication of the fact that the BPP could be the tight. It's also necessary. We'll talk about that later a little bit. So similar results were also studied in random matrix theory by these people. Okay, so implications, if this condition is true, then the null and the alternative are actually contiguous, meaning they're indistinguishable in the limit. So strong detection is impossible in this regime. Okay? Weak detection, so when strong detection is impossible, you can ask about weak detection, and it turns out that it is always possible, and the optimal error is given by this formula where this function is the complementary error function, is the tail of the Gaussian. Other consequences of this formula, you can actually compute KL between the two distributions. You can compute the TV, which is 1 minus this number. So these are all exact asymptotic formulas, and you can formulate non-asymptotic versions with error terms that go to 0. Okay, so our proof is not based on the second moment, but you can prove kind of similar results using the second moment method, and some people worked on this. Some of them are in the room, and also Marco presented yesterday on his compressed sensing, not compressed sensing, phase retrieval problem. The results he presented also are based on the second moment method. I'll present another method that is somewhat sharper than the second moment. So, okay, so is our result optimal? So there is a k that appears in result here. Okay, so I told you that it is always greater than or equal to 1. If in the case of Ising spins, if the U and V are plus minus 1, it turns out that this k is equal to 1, so the BPP threshold is tight. Otherwise, it is actually not. Let's look at the sparse Rademacher prior, where there are zeros so the prior has the coordinates of the UIs and VJs can have the value 0 with non-zero probability. Now we can look at what the likelihood ratio looks like. It turns out that there's a theorem by Mioran that tells you that if you normalize by n, then you convert to a certain function. There is a variational formula that you can write down explicitly and solve numerically very easily. It is quite easy to actually derive the fact that it is non-negative. And so we can actually characterize the problem using this function. So if this function is 0 in the phase space, alpha and beta squared, if this function is 0, that tells you that log L should be of more or less constant order, should be at least doesn't grow linearly with n. And when phi is strictly greater than 0, then log L will grow with n, and detection will be easy. So we can just look at this function, and it'll tell us a certain phase diagram. So the BPP threshold is the upper boundary of this banana. I'll tell you what this banana is. And the dashed region is the region where this function is 0. So we see for the Rademacher prior, the dashed region is strictly below BBP, right? So there is this weird sliver of parameters where you're below the BPP threshold. You don't see anything in the spectrum, but actually estimation and detections are possible. Okay, so the conjecture here would be that anytime the log likelihood ratio is sub-exponent or sublinear in n, it should be of constant order, and it should have the same fluctuations. So the entire regime of fluctuation, where the fluctuations are Gaussian, are given by the vanishing of this formula. And we don't know how to prove that. So that's an open problem that I think is very interesting. There is another question that I'm interested in is so I told you that 1 over n log L converges to a certain limit if the observation comes from the alternative, from the planted model, and now I'm asking whether it has a limit under P0. If there is complete noise in the observations, whether this thing has a limit. If it does, what is its value? Turns out that if like a positive solution or an understanding of this problem is a major open problem in Spiegel's theory. And there is also a very fascinating question of what happens inside this banana. If the parameters are inside here, I told you that estimation and detection are possible, although we don't know if they're possible in polynomial time. In fact, it is believed that nothing can be done in this region unless you have an algorithm that runs in exponential time. You can't sample, you can't estimate, you can't test. And that's a fascinating conjecture. So a word on the proof. So the proof uses techniques that come from spin-glass theory and that were originally invented to deal with this kind of model. This is called the Sherrington-Kirkpatrick model. And yeah, so per easy conjecture, the formula for the limiting value of this partition function. And later, 25 years later, Talleyrand and Guerra developed the necessary technology to actually prove the limiting formula, and those are the techniques that we use in this work. So I think I'm out of time, and that's it. Thank you.
Maybe one quick question while we have the speakers change.
What do you mean exactly when you say that this conjecture of the Ahmed?
So if alpha and beta are inside that sliver, then there is no polynomial time that can estimate, polynomial time algorithm that can estimate the spike. You can't sample in polynomial time, and if you want to detect, you will be stuck with weak detection. You can't have strong detection. It's impossible in polynomial. That's the conjecture.
Okay, great. Let's thank the speaker again.